what started the Big Bang?
Maybe that Big Bang took place within a larger universe.
The most fundamental nature of our universe, it isn't energy or matter or atoms, it's actually information. What I've always struggled with is the concept of nothing. How can something just come from nothing? Like, what is that nothing it's expanding into?
Oxford professor and best-selling author Vlatko Vedral is one of the world's top quantum physicists, tackling the most profound questions about our universe.
One of these two twins stays on Earth while the other one goes on a long journey.
That's the plot of Interstellar as well.
Exactly, Interstellar. That's called a quantum superposition. You could literally prepare an atom to be in one location and another location at the same time.
Is there any way that we can escape the death of the universe? Hi Vlatko, thank you for joining us.
Hi.
So the universe started 13.8 billion years ago, and ever since that humans have been looking up to the sky and asking, where did this all begin? So what started the Big Bang? What caused it? And is that even the right question to ask?
It's a great question, actually, and people think a lot about this in physics, in cosmology. We think currently, and that's maybe the best explanation that fits all the data so far, that there was a beginning to everything, as you said, the Big Bang, and actually even space and time was supposed to be created in this Big Bang. So these questions like what happened before, if you take this stance, are meaningless, as you said, because there was no time as understood with our best theory currently, the general theory of relativity, Einstein's gravity. So in that sense, that was the beginning of literally everything. Everything was created at that point.
But doesn't it have to be created into something? Like, and again, I'm just using my little human brain to understand this. How can something just come from nothing? Like, what is that nothing it's expanding into? What was there? And again, you said time began, but what was there before? What started this whole thing?
Yes,
what was the energy that kind of blew it all up?
I think it's an excellent question because we don't have an answer to that. That's what's interesting here, that's really work in progress. It could well be, as you say, that this was our own space and time in our own universe, and that's consistent with the picture so far. But maybe that Big Bang took place within a larger universe, and there are theories of that kind, interestingly enough. And even more than that, there are people who are making predictions. What kind of things would we have to see in the sky if this wasn't the first time that the universe was created? So this is all wide open.
So there's theories like the universe, there's like universe coming into and out of existence. There's also one that I read about quantum fluctuations, how in nothing, in the absence of anything, energy can just create itself. Do you mind like explaining a bit more about what that is?
That's a great point. That actually, in quantum mechanics, you have this famous effect called quantum tunneling. And what that means really is that a particle which encounters a wall and which, according to classical Newtonian physics, you could simply not penetrate. You don't have enough energy to penetrate the wall. But because in quantum mechanics everything is a wave, there is always a probability that the particle finds itself on the other side of this potential, if you like. It breaks through the wall, even though classically speaking it doesn't have enough energy. So there are all sorts of interesting suggestions there that the universe began exactly in this way. It was confined to a very small space, again, by potential and by forces that we currently don't understand. But then there was this fluctuation, quantum mechanical fluctuation, in which case space and time burst out in the open and start to expand. And the energy, as you asked, for this expansion is also unclear to us. We don't really understand the origin of this either.
And taking a philosophical turn, what I want to understand now is, can that ever be answered? So before space and time, do we have the tools to even look beyond that? Is this a question that's fruitless to ask? Because without space and time, how do we even go into it and see what started it? Are we just forever until the end of the universe? Will we ever find out what started the universe?
It's possible. All of these are wide open, actually. I think that maybe the thing to emphasize is that we have very few reliable bits of information from the early universe. You mentioned this cosmic microwave background, which are the fluctuations we now measure. But these are things that have happened a long time after the Big Bang. We are talking about 300,000 years after the expansion of the universe. And that's the kind of glow that we see after matter was created, it radiates, and that radiation comes to us, and now we can kind of measure some properties of this. So it's very one or two parameters that we really have there. And as soon as you have only a few things that you've really demonstrated experimentally, it means that there are a lot of theories that could actually explain that. And I think that's what we are facing. To be able to look beyond that, there would have to be a theory which suggests that there are some things that are observed which cannot be explained by just the ordinary Big Bang, unless you assume that there is something prior to that.
What's your personal take on what started the universe? Do you have a favorite theory?
I think we will find more. I believe that this second option that you mentioned, that there was something before that, and that we will find out more about it, is more likely to be the case. And I think more, Big Bang has been dominant for a while now, but I think many people, even those that pioneered this kind of theory, are now starting to ask further questions and change their minds. So I think we will discover a lot more there.
Is there any evidence as to what was there beforehand, before the Big Bang, or is it?
Not at present, none at all. I think some people talk about, for instance, the fact that if you look into different directions in the sky, the light that you receive, the intensity changes in a different way. And then you have to explain why does it look so uniform, broadly speaking, but then there are these tiny variations across the sky, that it's not completely isotropic, it's not quite the same in all directions. So that's what people say, okay, maybe this is something surprising, which is telling us that something could have happened before this. But it's very difficult to go beyond this.
Could we even measure that?
You're right. It could even be, and I think you raised a point, that it could be that we will never be able to access this. It could be that what we measure is some kind of equilibrium state that could have been created in a number of different ways prior to this, and we're just stuck with that. We can't go beyond that.
What I've always struggled with is the concept of nothing, like absent of space, time,
That's
nothing.
Right.
How can you explain this? What is nothing?
And
I don't want a philosophical answer. I want like a scientific
No,
one.
absolutely. I think that's another thing. As soon as you started to talk about vacuum and quantum fluctuations, it's good that you raised this point, because even that's not things coming out of nothing, because the vacuum, first of all, you're assuming that quantum mechanics applies to whatever existed prior to the Big Bang. And this is a huge assumption. We have no idea whether quantum mechanics was correct at that stage, if there was anything before that. So first you assume quantum mechanics, and then you assume this quantum vacuum, which is an extremely complicated concept in physics. So there are all sorts of particles being created and annihilated in this vacuum. So it's not quite a nothing. When you say quantum vacuum, it sounds like it's emptiness, but it's not emptiness in the sense of complete absence of even the laws of physics. So you assume quite a lot, and that's the best we can do in physics at present. So you're right. For us, nothingness already means quite a lot in many ways.
Is there a true nothing? Does that exist in physics or
and
science?
how would you even define it with respect to what would that be?
The absence of anything, like zero, like
there's a very famous American physicist called John Wheeler, who talked a lot about this origins of everything in the universe, and I think for him this was really the fundamental mystery. Where does all of this ultimately come from? And I think he talked about various concepts that could help us with this. But I think nothingness beyond. So if you really want to say, how do even the laws of physics arise? Ideally, you would like to start at a time where it was really chaotic. It wasn't really ruled by any laws of physics. And then gradually through this Big Bang maybe, or even maybe before Big Bang, you get the laws of physics to establish themselves. Because that's a big question. Why quantum physics, for instance? Why not some other laws of physics? Do they have their own origin? And I think in science, we don't know how to go beyond that. We simply assume here is the physics we have at present. Let's see what's the best story that we can tell about the universe with this.
And on that science can't explain this or is struggling to, do you think a reasonable explanation can be religion or spirituality or something that goes beyond the domain of the observable and things that we can
It's a great
experiment on?
question. Actually, it's a great question. And frequently when I talk about these things, I might come across as anti-religion in many ways. However, I have to say that uh, uh, yes, this question is very good, and the possibility is definitely there. Science at present is only telling us about a very small part of reality, and it could even be that our evolution, our genetic makeup is limiting us in some sense to understand the wider reality that's out there. I mean, after all, we know that's what happens with animals, right? If you look at apes, clearly they understand less of the universe. They don't do quantum physics, if you like, and many other things that we do. It could well be that we have a slightly bigger range of things we could do, but that there is a fundamental limitation. And the question is, would we even be able to know that? Could it be that we simply have arrived at the outer edge of what we can know, but we are even ignorant of the fact that that's the edge? How would you know if you came to that edge? So all of this is wide open. What I'm against with religion frequently are the simplistic accounts. We know that most of the major world religions, I would just say, are not sophisticated enough. They need to update themselves, and frequently they do. They acknowledge, if you look at, the Vatican, they would say, yes, we were against Galileo, we were against evolution, but now actually we take all of that on board, and in fact, they would even say what science witnesses ultimately is a kind of creation due to some deity out there. And of course, no scientist can really say that this wasn't the way things happen. We can't rule that out. But in science, unless you have a really dire need for that assumption, usually we find that we can explain things without any supernatural element of that kind. But we can't rule it out.
So just on the topic of religion, so a lot of people try to merge religion/spirituality and science. You'll be talking about people that talk about miracles in the Bible, miracles in the Quran, quantum meditation,
Yes.
all of these sorts of things. Do you think these people are quite misguided in the message they're spreading?
Yes, I think they're misguided because I think these are too simplistic. Yes, sometimes I understand if you say, oh, here is an account of a miracle there, and it looks kind of clearly impossible to us, but then someone comes along and says, but look at how weird quantum mechanics is. Maybe that event was really a quantum fluctuation. Again, you can never rule these things out, but if you just look at the logic of science, the coherence of the account of what we see, I would say this is exceptionally unlikely. I can't prove it to you that Jesus, didn't rise from the dead after 3 days, but somehow, everything we observe so far, there's never any need for any assumption of that kind, is the way to put it. So I think you can be spiritual. You can be religious in the sense that you think that there is a bigger reality. Maybe we will never get there. Maybe you can only intuitively make a connection with that reality, but not scientifically. All of this is possible. But I think the simplistic accounts that we usually get communicated to us are really far too simplistic somehow for our understanding, even at present.
So what role does quantum physics play in helping us explain the universe?
It's one of the two. It's a great question, actually. We have two theories in physics at present, and they're the best description of all the phenomena that we encounter in physics. The problem is that one of them describes the micro world, world of atoms, subatomic particles, particles of light, photons, and that's quantum mechanics. It started exactly 100 years ago. 1925, Heisenberg writes the first paper where he starts proper quantum mechanics. And we've had 100 years of experimentation. It's never been falsified. But to be fair, it's only been tested at a very tiny level. These are objects that we can't see with the naked eye. We really have to amplify all of these signals through various instrumentation. The other theory is theory of gravity, general relativity of Einstein. And it's also never been falsified in the last 110 years or so. It predates quantum mechanics maybe by 10 years. but it only applies to the macroscopic. And when I say macroscopic, we're talking about astronomy, really. We're talking about planets going around the sun, and then bigger and bigger structures, galaxies and clusters of galaxies, and so on. These two theories, the biggest open question in physics, really, is how to merge these two. No one has been able to quantize gravity so far. So in that sense, it looks very unclean to a physicist, because physicists are always looking for the simplest description, a completely unifying description. We believe that everything in the universe ultimately could possibly be explained through one set of laws. At present, we have two different sets of laws, and we actually don't know how to put them together.
So to summarize, in science, we have the rules of the really small, the atoms, and that's quantum physics. And then we have the rules of the really large, which is how gravity works and the solar system, and that's relativity. And right now in science, the open question is, they're two different set of rules. So how are they going to be unified? And are there any theories on how we can bring those two together to have one rule?
Many theories, actually, and that's probably one of the most exciting. Quite a lot of my research goes in that direction as well. So there are many views, and you can already see logically why this is possible. For instance, some people believe that quantum mechanics will have to be imposed on gravity, on relativity. You will have to quantize relativity, general relativity.
What does that mean?
It's a great question, actually. It's a fantastic question, because let me actually describe one thing which I think would help here. What does it mean even? In quantum mechanics, all objects we've tested so far can exist in many different states at the same time. That's called a quantum superposition, and that's really the most bizarre effect in quantum mechanics. So if you have an atom, you could literally prepare an atom to be in one location and another location at the same time. It has a probability to be here and the probability to be here, but really what it is simultaneously in these two places. And we've tested this. We can test this. It's called interference. We do all sorts of experiments to test this, not just with atoms. We've tested it with light. People have received Nobel Prizes for confirming this kind of behavior. And we've gone slightly in the direction of more and more complicated molecules. So larger and larger collections of atoms. But what we haven't reached, that's also interesting, is living systems yet. So if you ask me, could you make a virus or a bacterium to exist in two different places at the same time? We can't do that experimentally. There is nothing that a person like me sees against this, and I think it will be possible one day, but we can't do it. Now, when it comes to relativity, it's even harder, because we are talking about even more macroscopic systems. So I can give you one example. The signature effect in relativity is what's known as the twin paradox. It's not a paradox at all. It's been confirmed, but it hasn't been confirmed quantum mechanically, and that's the interesting thing. So the twin paradox says this, and it was in the early days, it was a criticism of Einstein's relativity. Someone said, look, your theory implies this, therefore it cannot be right. So the paradox, which is not a paradox, goes like this. You have two twins, and one of these two twins stays on Earth, while the other one goes on a long journey. So the other one takes a rocket journey to, let's say, another planet and comes back. And now what relativity says is that the traveling twin, upon returning, is younger than the twin that stayed behind.
That's the plot of Interstellar as well.
Exactly, Interstellar.
Yeah.
In fact, everyone should be familiar with it. It's
Yeah.
exactly right. The time goes at different rates in different places. And in fact, Einstein had this ingenious idea that gravity is not like other forces. It's not something pulling and pushing. Gravity is simply the flow of time that's different from one location to another. He almost completely eliminated gravity, and he said it's all about time. It's how time flows. Now, this has been tested with atomic clocks. People took an atomic clock simply on
What
an
is an
airplane.
atomic clock?
Great. It's probably the best way to talk about this is the most precise timekeeping device that we have. It really is precise down to a billionth of a second. If you start this clock at the Big Bang, it won't lose even a second up until now. So you run it for 13.7 billion years, and it's super accurate. It's amazing, okay?
And this clock actually exists. It's not just
It
a
exists.
theory?
No, it's
okay.
yeah,
It's a practical.
absolutely,
Oh, wow, that's
absolutely.
crazy. Yeah.
And the great thing, what I would encourage you to look at is if you look at YouTube videos, you have an atomic clock sitting on a table, optical table in a lab. And what you can see is that it ticks at certain rate. Now you can see the physicist raise the height of the optical table. It's putting the table in a slightly different gravity because gravity is different at different heights. And suddenly you can see the atomic clock change the rate at which it goes. So you can even tell the difference across 10 centimeters, even less than 10 centimeters of how strong gravity is in different parts. So that's amazing. And people took this on an airplane, went to Australia and back, and the clock that traveled on this journey really was younger, if you like. It showed less time than the clock that stayed behind in London.
So someone on Mount Everest at the top is experiencing time differently to us.
Even that's true. And that's all consequences of Einstein. Now I'm getting to the quantum punchline. All of this is classical standard relativity. It's been confirmed many times. Quantum mechanically, you can now take a single atomic clock. And as I said, you can put it in this is a single clock. There are no twins now. It's a single system playing the role of two twins, if you like, in relativity. You put this clock in two different locations at the same time. You put it in a quantum superposition. And if the clock is here, you send it on a journey and back. And if it's in the other location, you don't do anything to it. And the funny thing now is that when you bring them back together, it's still one and the same clock. It's in a superposition of being younger and older at the same time. This is mind-blowing. We don't even understand. We've never done this experiment. I'm advocating that we ought to, because we don't even understand what does it mean to be younger and older. How can it be? What time is this clock really showing? And that's kind of the main problem that people are trying to kind of solve and wrestle with in quantizing gravity. So like I said, I think we started by saying you can quantize gravity, but there are people, Roger Penrose may be the most famous advocate of this, who basically says, no, quantum mechanics will fail. So in the first scenario, you will force gravity to be quantum mechanical. So all things gravitational will be in many different states at the same time. Could be. But Penrose says, no, what will happen when we unify the two is that quantum mechanics will have to collapse and gravity will start to dominate. So that's why it's an exciting area, because in fact, many professional physicists are betting on different outcomes. Some of us think that quantum mechanics will win over gravity and gravity will have to become quantum. Some other people think, no, gravity will win and quantum will have to be gravitized, if you like.
So is it that both exist until they interact and then one overcomes the other?
Exactly. That is the key question.
And the one which wins will be the underlying...
It's a beautiful thing that you're raising, because yet another point of view is to say, look, they are happily coexisting, each in their own domain. What's the problem? Maybe that's the best we can do. Here we've got microscopic domain, perfectly quantum, no deviations. Here we got macroscopic, perfectly general relativistic, gravitational, all fine. But it's exactly your point that makes this difficult to maintain, because there will be a region where both quantum mechanics and general relativity may matter. And that's exactly the experiments that I'm working on are exactly in that direction. How do we test a domain where both must be taken? And then how do we take them into which theory wins, if you like?
You mentioned something earlier about, potentially different laws of physics. Could it be that on one hand, on the macro level, you have one set of laws of physics, and on the micro, you have another set of laws of physics, and that's maybe how can bring them together?
That's possible too, and it's possible that that would be the third road, if you like, to this solution. Of course, there may be many other roads that maybe we get surprised even more, but another possibility is that there is a bigger theory which encompasses both of these, and then in one domain it becomes gravity. In the smaller domain, it's quantum physics, and it's all perfectly fine in that sense. So that would be, in fact, that's how we usually, that's usually what happens when you have a revolution in physics, that the new theory is much more general than the previous one, and you recover the previous theory in some special domain, some special limit. That's what happens with quantum and Newtonian. That's possible.
And what I'm wondering is, why do we even need one unifying theory? Isn't this a limitation of like humans, where we try to reduce everything to in complexity and Occam's razor, there must be one? It could just be that the universe was not created for us to understand it, and they just exist, as he said, different rules for different matters of size and stuff.
Possible.
And could it be
possible.
that we'll never unify?
Yes, absolutely, absolutely. It's just, you know how the human spirit works, that you kind of, you're always optimistically hoping that there is more to be learned. And at the moment, we have no reason to stop, really. But it could be, as you say, that we just keep discovering more and more, but actually we're still stuck with the two theories and we never come up with a unifying one. It's all wide open.
Hey guys, thank you for the support that you've given to the Whitelist podcast. We've received over thousands of listeners across YouTube, Spotify, TikTok, and Instagram. Thank you so much. Please like, follow, subscribe, and we can get more great guests like Vlatko Vedral. So what I want to move to now, Vlatko, is the thesis of your book, which is that the most fundamental nature of our universe isn't what we were taught in school. It isn't energy or matter or atoms or the soul or anything. Yes. It's actually information. Can you explain what the hell that means?
Yes, I like that thesis, and I think that even somehow unifying quantum physics and gravity, as we said, will be aided by our understanding through information theory. I think that there is a lot of mileage that we will get out of that. But let me just go back to the beginning. So traditional, if you open Oxford Dictionary, or I don't know, one of those books, it defines physics as the study of matter and energy. So if you ask yourself, what are the fundamental constituents of the universe? Always matter and energy.
I think that's what we always
taught.
All
of us. All of us. We grow up, we learned it in school, and
like the most like if you take everything and you add its most fundamental at the starting block, it's a mix of matter and energy.
That's it. And I think modern physics is telling us to go beyond this. So in some sense, you can already see this on the experimental side, that the deeper we go into the micro domain, the more we discover there. You know, we have this theory called the standard model, but it's a very heuristic way of unifying all the forces other than gravity so far. So gravity is still outstanding there. But this theory tells us that there is a certain number of fundamental particles that we have. However, as we invest more energy, as we come up with more sophisticated experiments, we tend to discover that there is a lot more happening down there. So there is no guarantee at all that the number of particles that we have at present is actually the ultimate number. You know, the three forces that are quantized, if you like, plus all of this matter that couples through these forces, exactly as you said, matter and energy. So somehow it seems to me that it's better to change this picture and talk about atoms, not in terms of what is the smallest unit of matter or energy, which is how we traditionally think about this, because it could well be that there isn't the smallest unit of matter. Maybe we just find more and more as we proceed with our experiments. It seems to me what quantum physics is telling us is that we should be thinking about the atoms of information instead. These would be called the bits of information. Always bits, in the sense that the atoms of information are the questions to which the answer is always either a yes or a no. And that's what we call a bit of information. It cannot get smaller than that. So you ask a question, is an atom located here? It's either yes when you do the experiment, or it's a no. And that's kind of your fundamental bit of information. And it's interesting that in quantum mechanics, even if you look at the structure of quantum mechanics, it really feels more like a theory of information than it's a very abstract theory. It certainly doesn't talk about atoms and energy in these axioms, but what it does talk about is what will happen when you make a measurement on the system. And the fundamental atomic units, if you like, of information that you get from your measurements are these bits of information.
So is it fair to describe the universe as almost like an information processing system or unit where every time atoms and things are measured, it's something or information sort of manifests?
Yes,
in
I
that
think
sense?
that's the best picture that we have at present. And I know that, people say, and of course it's a very dynamical picture that we have because science always is evolving. But with Newton's laws, deterministic laws, tell me where the planet is now and how quickly it's moving, and I will tell you where it's going to be in a million years' time. That's how deterministic it is. People always thought at that time that the universe is a huge clockwork. Maybe wound up and created by
God,
God,
play
if
dice.
you like.
Yeah.
That's it.
God doesn't
Exactly.
play dice.
Exactly. God doesn't play dice there at all. Then with the advent of maybe thermodynamics, there was the Industrial Revolution, steam engines, then people thought about, maybe the universe is like a big steam engine. That was the right metaphor at that time. But I think now, with the advent of computers, information processing, especially now quantum computers that we're trying to build, it seems to me the right metaphor for the universe is a big computer, a big quantum computer in this case.
I want to take it back and focus on information. And what I want to establish is what is information. So it's the answer, it's a yes or no to questions.
Yes, for information, what you need, I think this goes beautifully back to this: God doesn't play dice, or God does play dice, whichever side of this question you are. Shannon, an American engineer, actually, he worked for the Bell Labs. Claude Shannon was the person who wrote the first two formal papers defining information. And it's actually very simple to understand. So he wanted to make a definition that's extremely robust and simple and very clear. Because I think if you read lot of literature nowadays, people use information in all sorts of different ways. And frequently it carries extra degrees that Shannon wanted to eliminate. So Shannon wanted to say it doesn't matter how you communicate, information should be independent of that. So which language we use, it should be relevant, which actually is why he started to use zeros and ones. He said the ultimate language, in terms of which you can express everything else, is simply strings of zeros and ones. I don't need anything more than that. That was the assumption number one. Assumption number two was that all you need to know now is the probabilities with which zeros and ones will happen when you observe your string of bits. And he said, once you give me this probability, I can then find a formula for information. It's actually very simple to understand. This incidentally goes back to the ancient Greeks. They had this idea already, and their idea was this: if something is really unlikely to happen and yet it happens, this carries a lot of information. Whereas if something is very likely to happen and it does happen, that doesn't really tell you anything. So a perfect example of that is, sun rising tomorrow. I think all of us expect the sun to rise tomorrow. None of us will be surprised. No one will be writing about that event because we all expect it with a unit probability, more or less. Whereas something that's really unlikely, and I think this, of course, is, if you had I don't know, a month of sunny days in London, right? It's highly unlikely that you won't get a drop of rain. This really would be surprising to you. And you'd be starting to think, why did it happen? Is there some environmental change there? You'd be starting to look for causes and things like that. And in science, these kind of events are also extremely important because we are looking exactly for evidence. If we want to overthrow a theory and show that maybe there is something wrong with general relativity or quantum mechanics, we are really looking for experiments that would falsify this, no matter how unlikely we think that might be from the current perspective. So somehow more information always associated with smaller probability. That was Shannon's logic. And there's a particular formula that we don't need to worry about. It's a very simple mathematical formula, but the key is this inverse kind of relationship with probability.
So the core of information is the probability of something occurring, could you say?
Exactly like that, yeah.
Okay, and then my next question would be...
And ultimately, it goes back to these bits, that ultimately any complex event, you can always break down to a sequence of bits. first this happened or didn't happen, then the next thing happens and doesn't happen. And when you add up and put all of these bits together, that gives you the total information for that.
Cool. So that's information, but how can that exist without it being imposed on matter and energy? For example, let's look at that book, right? That book is a book of information, right? But without your consciousness, without the paper, that information doesn't even exist without the energy and matter to represent itself on. If that question even makes sense.
It does. It makes a lot of sense.
I'm just kind of thinking through this and trying to work it out.
Absolutely. And I think this is one of those kind of chicken and egg problems in science, and science is full of that. What comes first? So you're right that one perspective is simply that information has to be encoded into a physical system. So you have to have some atoms there, some light there, and then you're going to use these atoms and light as your bits of information. And then, of course, you're going to use the laws of physics to process this dynamically in some shape or form. What I try to communicate in this book is that maybe we should change this picture and think that information could somehow have an independent existence prior to that. And then it gets imprinted, if you like, on matter and energy, which arise out of this information initially. But you're right, both of these perspectives are possible.
Could it be codependent as though...
It could even be codependent, you're right. That would again go back to John Wheeler, who loved to talk about it like that it's when we engage with the universe, that information that arises out of us experimenting with the universe is what creates our reality, actually. And I think he even thought that the laws of physics come out of nothing in this kind of dialogue, if you like, between humans and the universe. It's very interesting.
If information was independent, though, like
Yes.
how would that be encoded? Where would it
Yes,
be
good
stored, and
question.
what form would
Yes.
that take?
And
So-
I think you're right that these questions, you always in science come up against these questions. It's a very similar question, logically speaking, to where do the laws of, if I claim to you that there was a vacuum fluctuation, you would say, but wait a second, that already obeys quantum mechanics. Where were these laws encoded if you claim that there was nothing, there was no space and time prior to that? So I think we have exactly the same problem with information. Somehow you might then have to imagine that there is an origin of this information. There was almost like the first bit of information that got created in the universe, and then we evolved that from that point onwards.
What role does the observer play in these manifesting themselves? Like the example would be these rules only exist while somebody is observing them, and they don't exist outside of that. Is there any kind of truth to that?
That's also a good question. Clearly, we are the only species that we know that does science this way and that discovers the laws of nature in this way. Highly mathematical. There might be other ways of doing this. As far as we know, so what gives us confidence that these laws are somehow independent of humans, that the universe existed the way we think it existed even before we came on the scene, maybe a million years ago, in terms of evolution, is that when we look at distant parts of the universe, they really so far perfectly conform to both gravity at that level, as well as all the signals that we get are analyzed quantum mechanically, all the basically intensities of light, the fluctuations and so on. So we don't see any deviation whatsoever. When we look at the records of the past as well, it seems to us this all conforms to the laws of physics. But of course, in physics, it's always indirect in this way. It's just the best, it kind of looks like the cleanest account that we have. But it's very difficult to prove anything directly as you do in the lab, simply because obviously there was no one there to witness any of that. So we can't say anything about that.
Yeah, so just building a little bit more on the whole topic of observers. So in your recent Substack article, you said that physics actually doesn't require observers at all. But then in your book, Decoding Quantum Reality, you spoke a bit about sort of Wheeler's ideas of, co-creation.
That's it.
Yeah. Was that more just you exploring these as an idea, and you think that actually observers aren't necessary, or do you think observers maybe are?
They are not necessary for one specific thing. I think I had a very specific thing in mind in quantum mechanics where people claim that quantum systems behave in this weird way. They're in many different states at the same time until we look at them. And this happens to be true.
And then when
So
you look at them, they pick a state to
that's
remain
it.
in.
And they pick it randomly. This is the one where Einstein complained, saying, I can't believe that God plays dice with the universe. How can this be random? There's got to be some rule. And as far as we know, there isn't any rule. And that's what suggests to a person like me, this is exactly when we reach this atomicity of information. When you get randomness is when you are asking these basic, fundamental, smallest questions that are possible to ask. Is it going to be here or not? And it seems to us that this really is perfectly random in the sense that you're almost creating new information when you do that. Prior to that, your information was that it's really in two places at the same time.
And how do we know that it's in two places? What is it that
Great
we're measuring
question.
to
Wow,
know?
it's a great question. There's so much confusion about this when you talk at this level. Yes, how do we know that it's in two places? We know, and in fact, this goes to the core of quantum technologies. We know for the following reason: you can perform one operation to the system in one location, and independently, you can do something completely different in this other location. And when you then measure them together, these two actions, you will see that they took place simultaneously, that both of these are imprinted in the final behavior. So that's known as quantum interference. So that's a bit like making your computer exist in many different states. In one of these states, you perform one operation, 3 plus 5. In the other one, you perform another calculation, then another calculation. And we know that all of them took place simultaneously because when we measure the output, somehow we know that the consequences are there of all of these actions. But the interesting thing is, if you really insist on observing the system, you will, and that's what quantum mechanics tells us, you will only see it in one of them. You have to do something more sophisticated when you interfere these possibilities.
So that seems crazy, and it brings me to when I was younger. So when I was, I think 15, 16, I used to read a lot of like pop science articles, and it constantly used to paint quantum physics in this kind of mysticism. So quantum physics can prove an afterlife. Quantum physics can prove God. And there's this quirkiness and this kind of mysticism and this craziness to quantum physics that kind of gets misrepresented. But going like deeper, you've got people like Roger Penrose who say our consciousness is linked to quantum mechanics in some sort of way. So I want to hear from you. What's the link between consciousness, one of the craziest things that I've read about, and quantum physics?
It's a great question. I think we have no evidence at all that there is anything quantum in consciousness at present. On the other hand, we don't understand how humans think. If you think in terms of computation, it's very difficult to reproduce. In fact, at present, it's impossible.
It's the hard problem of consciousness.
It's
like
exactly
David
the hard
Chambers.
problem. None of our AIs are anywhere near. Any AI engine at present is really just a very sophisticated, very fast search engine. Ultimately, it's just cracking a lot of these possibilities and just coming up with one of these answers that you require. And it's all to do with speed. It really doesn't mimic, as far as we understand, how our brain works. So I think coming back to this question of changing reality, what I wanted to, the reason why I was against the fact that consciousness is any different to any other physical system is that you can destroy this quantum superposition. You can collapse the quantum system into one place, not just by looking at it, but by simply interacting another quantum system with that system. And that's what makes me think, well, there is nothing special. Yes, it's true that humans have the ability to collapse quantum superpositions to a definitive outcome. But in fact, in quantum mechanics, any other system, if you have a single quantum bit, if you have a single system in two places at the same time, all you need is another system that gets entangled. In Schrodinger's language, this is called entanglement, when you have a superposition at the level of two systems or more systems. And that other system doesn't have to be conscious, doesn't have to be sophisticated like ourselves, doesn't have to be even living, doesn't even have to be a computer. It could be as simple as the first system. And it's enough that it gets somehow into the same superposition with the first system, and you've lost quantumness, if you like, at the level of each of these two. So it's very interesting that when people say, oh, we can change reality by looking at it. Yes, we can, and we do, but so can anything else. And that's kind of where I think that's beautiful, because it just gives us a unification in this sense.
So both conscious and non-conscious observers can
That's
basically...
the punchline.
Yeah.
That's the
Okay,
punchline.
got you.
Now, whether there is something special in conscious observers, yes, it's possible. And it's possible that the reason why our consciousness is different to computations that we have in present, maybe there is some quantum magic going on, but we really have no evidence that. There are some ideas. You mentioned Roger Penrose, microtubules, right? He's thinking...
Do you mind explaining that idea a bit more?
Yeah, I think the idea there is that it's exactly this collapse of the wave function. So some molecules inside your brain, and he identified microtubules, I think because they matter biologically in various anesthetics. I think these are the things that respond to anesthetics and basically to when you disable your kind of awareness. So, intuitively, maybe that's where consciousness does play, resides in some sense. But it's it is a conjecture. It's a wild guess at best. So I think what he's thinking is that prior to some kind of introspection, let's call it, prior to introspection, these things can be in many different states at the same time, and they're processing ideas simultaneously. But then as soon as you ask yourself what it is that I'm thinking now, suddenly there is this magical collapse of the wave function, if you like, collapse of the quantum superposition, leading you to a definitive outcome. And actually many people have speculated that our thinking does resemble a little bit the quantum logic. That you're doing many things subconsciously at the same time, and then as soon as you want to think about it really and be aware of what you're thinking, you always crystallize a single outcome, if you like. Collapse it. That's kind
And from my personal experience, I would agree. I don't know about you guys, but I don't know what I'm thinking about right now. There's everything's going on until I focus it, and then it seems like I have this direct focus. And I don't know what my next thought's going to be. It's this kind of it could be any thought until I, focus on the thought, and that's so. I don't know if you guys, as a personal reflection on your thinking process,
yes, absolutely,
if you see similarities with
absolutely.
that.
Mm-hmm. David Bohm was a guy who wrote a lot, one of the pioneers of quantum mechanics, and he wrote. There's a whole chapter in his. It's a textbook on quantum mechanics, but in one chapter he asked this question: what does this all mean? How do we actually understand things being in many different states? And the analogy that he gives, although he may think there's more than just an analogy there, is exactly our thinking. That while you're thinking, somehow you are not aware of each of the, you're thinking, what am I going to do tonight? Am I going to stay home, have dinner? Am I going to go out, have fun, and all of these things? You're not really aware of all of these details. And then at some point, suddenly, you've made that decision. Oh yeah, I'm going to go out and have fun. But it's actually very hard, and that's what quantum mechanics says. You can't now retrace simultaneously these two paths backwards. It's a random outcome. You just got one outcome, oh, it's definitive now, but you can't quite explain to me exactly how you came to that conclusion. And as you start to explain it, in fact, you engage in a creative process yourself. You probably
making up how you got there.
You actually created it. Exactly right.
And sticking with consciousness, I just find consciousness so fascinating. So with Descartes, I think therefore I am, people who had this dualist view of consciousness was something separate to matter. But now all scientists are pretty much in agreement that no, it has to be material.
It seems to me
What's your personal thoughts?
Yes, I think so. It seems to me that as a physicist, you would really bet that different states in your mind, in your brain, are somehow encoded into physical systems. So yes, whether it's a classical computer, whether it does, whether it's sufficient to have Newton's laws, or maybe it's quantum computer as Penrose thinks, or maybe even more than quantum, there is gravity, collapsing things, and so on. I think most scientists would agree that it's a physical machine. It's somehow physically encoding all this information processing. We have no idea how this is done. And I think that's the main difficulty with the AI. Like I said, what we do with our artificial intelligence is nothing similar to basically how the brain operates. The brain seems to operate in a very delocalized, diffuse way. Many things happening simultaneously in different parts that communicate with one another. Our computers are the opposite. There is a central processing unit, and that's the guy that does all the work, then sends, and everything is fed back into the CPU. It's the von Neumann architecture, if you like. So basically, how people thought about computers 100 years ago is exactly the architecture we have now. But it seems biology does this very differently, in fact. It's somehow spread across, maybe even just beyond the brain, right? The signals are coming from everywhere and so on. So it's not clear to us even how to understand the logic of mental computation.
So if consciousness is a quantum process,
Yes.
is there any way that we could ever test for that?
Yeah,
Design
that's
experiment?
exactly the question. That's exactly what you want to ask. Because, first of all, in fact, that's how I'm thinking as well. When someone says microtubules, the first question you even ask yourself is, can I prove experimentally that they can behave quantum mechanically even under very controlled conditions? So before you even venture into testing directly the human brain and whatever a neuroscientist would do, you want to extract these microtubules, put them under extremely controlled conditions. What that means is you want to eliminate any noise, anything that's coming from outside. You want to isolate them. You want to cool them down to very low temperatures. So in physics, when we make quantum computers, we are going down to the billion times lower temperatures than the room temperature. These are really tiny micro Kelvin, as they call them, nano Kelvin, even in many of these. There are like 6 Nobel Prizes behind getting down to these temperatures. If you put a microtubule in this environment,
So, do you mind just explaining what a microtubule is?
a microtubule is actually, interestingly enough, because when I tell you what it is, it's not obvious at all that it should play any role in consciousness. And that's why I'm saying it's kind of an educated guess, but maybe there is nothing to it. It's a very small organelle that matters in the cell division. So these are the guys that when a cell divides, they somehow aid these chromosomes and split the biological information into 2 new cells. So they are very important in that case. But I think because some medical research tells us also that they change their functionality under anesthesia, then people are thinking, oh, wait a second, if that's maybe the key element to how we lose our consciousness, if you like, how we switch it off, then maybe those are the components that are also relevant here. So I don't think there is much more evidence than that this really matters. So it's a very, for our purposes, it's a complex molecule, but still tiny, much smaller than a human cell, which is why in physics we are thinking maybe we can do some quantum experiments with this. Maybe, for instance, we can hit it with a laser, excite one end, see what happens when information travels down this. Does it travel in a superposition? Does it follow many different paths at the same time? Is it like a mini quantum computation? And if you don't get that under super controlled conditions, there's no hope that this does anything quantum in the brain. So somehow in science, we are trying to rule it out, at the simplest level. Then if that passes that, then we ramp up the temperature. Then we say, oh, it's quantum there. What if we increase the temperature? Is it still quantum, and so on? So that's how some of these experiments work. And then, of course, ultimately, what you'd really like to do is to do it exactly in the context where it matters. You want to monitor a human being while they're thinking and see whether these, whatever the units that are relevant for this are in quantum superpositions.
And let's say we've discovered the framework for consciousness. We've been able to map it where, like, if you add this up or you do this, that's consciousness. There's a big talk about AI and generative AI and AI essentially becoming conscious. Is that the missing step? If we can understand how human consciousness works, apply it to AI, that will just transform the world.
Yes, I think you're right. Somehow using the word intelligence in AI is probably not appropriate, because it's, if you have human intelligence in mind, how we really come up with solutions to various problems, that's not what AI does. It really has to be fully pre-programmed to take these steps that it takes. And of course, it does take them much, much faster than our biological brain is capable of, but it doesn't do it in this way at all. So I agree with you. I think there is a big missing component that we don't understand if the goal is really to create an intelligence of our kind. So for instance, AI could never come up with a new law of physics. No matter what you feed into this engine, I don't think it will get that level of creativity where suddenly, something switches on and it starts experimenting and making conjectures and invalidating them and so on. It doesn't do that. It can work, chess is a great example of what it does, and it does it purely because of the speed. It's pre-programmed to have, a certain number assigned to each piece in chess, so pawn is worth 1, whatever, bishop is worth 2, and so on, queen is worth 10, and so on. And all it does is a brute force evaluation of as many possible ways to proceed as there are. And because the clock speed of this machine is extremely fast, we're talking about more than 1 billion operations per second. We're talking about 10 to the power of 12, 1,000 times more than that. Whereas our brain operates almost at the level of a second. It takes us half a second to think about a new thing, okay? So there is the best chess player there thinking half a second, another half a second. Whereas this guy has crunched already God knows how many ways to proceed. But it's simply brute force.
Yeah, I think the best chess player in the world, Magnus Carlsen,
That's
he
it.
can't beat the pro level on a computer game.
Cannot.
Because he
No
just does
way.
everything much
But it's
faster.
purely because of the speed, not because this guy is capable of independent thinking and so on. It's really been already pre-programmed. That software cannot go back and say, wait a second, why is a pawn given just 1 unit here, which is what a human would say, wait a second, is that the right way to assign numbers? But I think this software can't do that. It can't say, why am I programmed this way? I want to change that. It's just not in the repertoire of possibilities. And until we discover how is it that we humans can really genuinely do something new, we don't understand that, I think.
It seems like with creativity and breakthrough, there's almost like a certain randomness that
Yes.
comes with that. And
Yes.
it's like with artificial intelligence or quote unquote
Yes.
intelligent systems, they're light years ahead of us when it comes to things that have already been
Absolutely.
done. But they can't, there's no randomness
No.
there. There's no unpredictability.
No, not
So-
at all. And it could go back to exactly, that's why it's very suggestive that maybe there is something quantum there. Because whenever we have a new idea, none of us can really explain how this happened. And frequently it happens when you least expect it. You're really trying to think hard about a problem, you're getting nowhere, then you take a shower and lots of people say, oh wow, look at that. That's
Yeah.
the eureka, that's it. And why does it happen then?
Yeah.
And is it because we switched off? Maybe when we think we're too deterministic, maybe we need to relax and switch off for some quantum things to take place, if you see what I mean.
Yeah.
It is possible.
I think even the structure of benzene came to the discoverer in a
Yes.
dream,
Yes,
basically.
yes,
Yeah,
it's
so it's
amazing.
really
It's
weird
amazing.
stuff there.
Indeed,
So,
yeah. The
But-
table of elements as well. Yes,
Yeah.
that's right.
But I just want to, like a rebuttal to this is essentially sometimes you can make discoveries through pattern recognition. So for example, let's say the heliocentric model, like the model of the universe, you don't need to have consciousness to understand that this is like where the Earth's placed, this is a science. So maybe not all maybe AI could make certain discoveries that are based upon, like especially with a large language model of just reviewing loads of information and seeing something that humans through bias or our own weaknesses can't pick up.
Yes, I think you could say that we are biologically, because the way we evolved, what we do is still extremely specialized. So you could say, yes, we too are programmed somehow naturally through evolution, but that's taken place over the last 4 billion years. So there's a lot of programming that's gone into, so to be fair to computers, as you say, to AI, maybe give them a bit more time. And as they explore all of these possibilities, maybe it will somehow emerge. For me, it's very difficult to see. I think we're missing a key component there, but it could be. That is possible too.
So I want to move on to another part of the book, and it's when you talk about determinism versus
Yes.
free will /
Yes.
randomness. And this is
Yes.
something that me and Ish debate
Yes.
all the time.
Yes.
I'm a determinist
Yes.
and he's a free will person.
Yes.
I'm in between, but yeah.
And when you
Yes.
read about free will, I think it's a fundamental misunderstanding of quantum physics. And so this is my theory. The randomness you describe in that book isn't controlled randomness, it's probabilities. And what free will is you making a choice. So just because the world isn't from on a quantum physics level deterministic, it's random, that doesn't mean you have control over what that random outcome is. And therefore, there is no role of of free will in quantum physics.
Yeah.
Do you agree?
Yeah, it's a great argument, and I'm on that side of things as well. I think it was a big debate in the early days. If you go back to the 1927, so 2 years after Heisenberg's paper, there was a famous meeting, Solvay meeting in Belgium, in Brussels. And what happened is that they debated all of these issues. And I think someone raised this point that, oh, look, it liberates us from the Newtonian determinism, which obviously was bad for free will.
The idea that God doesn't play dice,
That's
you can
right.
predict everything.
That's it. But then, as you say, a genuine randomness, and quantum mechanics really suggests to us that there isn't an algorithm for predicting which outcome you would see. That's kind of equally bad for free will, if you say. How does that then, I really want to have a high probability of success when I decide to do so. That's what you think free will is, right? Now I'm going to make a decision to do this, and look, I'm doing that because I think it's very likely that something will happen. But actually, fundamentally, it's really random. These basic bits that everything is made up of, you have to acknowledge that there isn't a place for free will there either. So I agree with you. Science does not explain that. In fact, even the definition of free will, it seems to me, is like we don't know what it really means. We all feel that we're responsible for our actions and that we could have done otherwise, but it's not clear really what that means. It's not even clear how you would test it. So how would you really, what kind of experiment would you do to convince me, for instance, that you have free will? Now I really acted freely. It's difficult.
On the topic of sort of randomness within the quantum sphere, is that just a lack of data points? Do you feel like maybe that's a point where in the future, if we have a sufficient amount of data, that actually determinism will also conform?
It's a great question. And in fact, that's people like Einstein were in favor of that. It's called a hidden variable model. That basically hidden means that there are variables that we are not aware of. And if only we understood them and we realized that they exist out there, you could actually predict things perfectly. Now, the experiments we've done so far rule out certain types of hidden variables. So let me be a bit more specific. If you, these are the kind of the latest Nobel Prizes in physics, where people take two systems that are entangled. They usually take two photons, two particles of light. They separate them across vast distances, kilometers, sometimes hundreds of kilometers, in order to measure them independently. So you want to get a detector to measure one of these photons, another detector to measure another one. And the reason why you separate them so far is that you want to make sure that the measurement here cannot possibly affect the measurement over there. The only way to affect it is if information traveled faster than the speed of light. So that's where we trust relativity, that nothing really travels faster than the speed of light. So these experiments are really telling us that there are no hidden variables at the level of these systems locally, which means you can't have something that's localized in the vicinity of one of these photons and in the vicinity of the other one that explains this. We know we rule them out. But that doesn't rule out that there are no global hidden variables, as you would call them, at the level of the universe. So that's always possible.
So to describe this further, it's kind of like, let's say at the start of the universe, we had this massive supercomputer and we put in everything about like whatever that little like nucleus of energy had. It could predict us having this conversation right now because it can predict the speed of which the energy would travel. And then taking it to something a bit more mundane like a coin toss, which seems random. if you could account for where the atoms are, the velocity of like
It's
speed,
exactly-
Wind
you could
speed,
predict
yeah.
if it's
Perfect
going to
description,
fall
yeah.
heads or tails, and the
Yes.
person doing it and how their like finger is shaped.
Yes.
You could predict everything.
Absolutely.
And right now we're questioning whether there are hidden variables that would make something that's
Exactly
random in quantum
right.
physics
Exactly.
actually deterministic.
Exactly, and the formally it's called superdeterminism. Exactly what you described. So some people who counter quantum mechanics and they say, wait a second, yes, there are these Nobel Prizes, yes, they proved something, they ruled something else out. What they didn't rule out is that all of this is written somewhere in the universe very far back into it. So even if these two systems cannot communicate with one another during your experiment, as you measure them, if you go back far enough, there will be causes which could potentially affect both of them independently. So they can't affect each other, but there could be a mutual cause right at the beginning of the universe, if you like, which somehow explains all of that. We can't rule that out.
So Vlatko, we've spoken about the start of the universe.
Yes.
We've spoken about the rules that govern it
Yes.
and our experience through consciousness. Now I want to touch up on quite a nihilistic topic, but the end of the universe. So in your book, you
Yes.
describe whether it's going to be a heat death. You describe entropy and how information is going to
Yes.
keep getting more and more complicated,
Yes.
leaving. Do you mind giving us a theory to how the universe is going to end?
It's another beautiful topic because
I think it's quite depressing, not beautiful.
it is depressing as well in a sense, not directly because all of these times that we're discussing are really long into the future. I don't think any one of us will exist.
We're planning to live forever.
Yeah,
with,
that's it. Unless
Brian
biology.
Johnson.
That's
Yeah,
it.
yeah, with Brian Johnson. we're
Exactly.
gonna live.
Genetics maybe catches up with this. yeah.
Apparently, it's like if you stay alive to 2050, somebody's made a prediction, like a famous
Ray Kurzweil, maybe.
you will
Yeah,
live
yeah.
forever. So
Yeah.
we'll see if you make it.
I
Like, with us.
went to a conference. I'm digressing a little bit, but
Yeah.
I went to a conference. I think it was in Sicily, and I landed, and I started chatting with another person. I didn't know him, but I thought this was someone coming to the same conference. And we start talking, and I go into my physics, quantum physics, and the guy looks at me and says, "I've got no idea what you're talking about." And I said to him, "But wait a second, you are coming to our conference." And he says, "No, I'm here on another conference, and it's biology." And so we start chatting, and he says to me, "Do you know that you are the last generation that's going to die?" So this was one of those biologists. That's it.
Yeah.
I think he tried to kind of scare me, right? At that moment, I thought that would be really unlucky, right, to be the last generation. But I think biologists are, if it really is all about error correction, if it is the wear and tear of our genes and the replication that's the key to aging and dying ultimately, then why not? Maybe we could prolong it as much as in which case maybe what we're about to discuss, the end of the universe, does become relevant.
So as things get more and more information, they decay and they become more disorderly, like information. So even though we can fix the wear and tear, us gathering more information as we exist will make us more unstable.
You're right. And there could be a fundamental limit there. Maybe this is something we cannot error correct fast enough. By the way, for quantum computers, the same question is there. We can handle small number of quantum bits up to now. You hear places announce like 100 quantum bits, 1,000 quantum bits. And of course, we need many more quantum bits to do proper quantum computations. But we don't know if we will ever get there. And it's exactly this race against the environmental influences, the unwanted influences that are continuously increasing the entropy and disorder, and us trying to do things quickly enough and to repair it. And maybe we will never get there.
So let's say we live forever. Let's just
Yes,
take that
let's
for
say.
granted. When are we going
What
to die?
happens? Yeah.
What is the culmination of this universe, of this podcast, of this discussion?
Yes, one possibility, and that becomes increasingly likely now. It was in the past, if you ask these questions, even 20, 30 years ago, people were discussing all sorts of possible universes. So, there was a big bang, things are expanding. We don't quite understand why they're expanding and what gave this initial momentum and so on. But people were quite open to the possibility that the expansion will slow down and gravity ultimately will just bring everything back into the big crunch as it's known. So this would be like an oscillating universe. People were even talking about Big Bang, then Big Crunch, then followed by another Big Bang and so on.
Over and over.
Over and over. And there are still some people who advocate this model in a larger universe now, that we're just a small part of a larger universe that may be still undergoing something like this.
Just on that,
Yes.
would one of the counterpoints be that with the gamma and the way we record energy, we don't see it going back in? Because if it's the same universe
we
that's
don't- we don't see
contracting
that
and
at all.
expanding, we would have
Redshifted,
records of
yeah,
it going
that's
in
it,
and out.
yeah.
Right now, we just
Yeah.
have records of it going out.
Yes, indeed. And people even raise fundamental objections. They say, wait a second, the entropy is increasing with the expansion, but now are you telling me that time is going to start going backwards as we contract? So there are all sorts of interesting questions, you know? Like, what would it even mean that the time flows backwards now? You're doing the exact opposite for the second half.
Benjamin Button sort of.
That's
Yeah.
exactly Benjamin Button. I think that's what is. So now, as we know, and just remember always that there isn't sufficient data in that domain to be as confident as we are about atomic physics. So we understand the behavior of atoms obviously far, far better. The experiments are much more sophisticated. We can control all the parameters. Here, as far as we understand, the expansion is accelerating, if anything. So it's not even a constant rate. It's actually expanding faster and faster, which means that at some point, that's where this heat death becomes one possible scenario. But in fact, even before that, the expansion will move even the nearest galaxies beyond what we call the event horizon. So we're going to become more and more
Do you mind
isolated.
explaining what the event
Indeed,
horizon
the
is?
event horizon is the point beyond which even light cannot reach us anymore. It's receding so quickly that even if someone tried to send light from that point, it simply wouldn't be fast. Even the fastest entity in the universe, light, could not reach us. So even the closest galaxy to us, which whatever distance it is now, it's still far away, of course, for our technological ability. But we can see all of these things. It could be that there will be time when we won't even be able to see these objects beyond a certain distance. But it's still not the ultimate state of the universe, because you're going to continue to expand. Ultimately, all the matter would disintegrate somehow, and we would reach a state of equilibrium, which is why it's known as heat death, that everything reaches the same temperature, if you like. And once you have the same temperature everywhere, nothing useful can be done. I think in my book I was trying to talk about it as some kind of information processing death, in the sense that you reach the point beyond which you can't get useful information. Whatever you do keeps you exactly in the same state. You can no longer get even a single bit of information. There isn't anything different that can happen now, a different outcome to surprise you, if you like.
And so my next question is, how does information die? Because again, if we go back to the definition of it, it's a yes or no. How can that just not exist?
It's a great question. I think information in this scenario, you wouldn't talk about information dying. You would just talk about the ability to process to get different information, and you would just say, no, I'm stuck with whatever it is now. I can never get anything new. And that would be kind of the state of the universe from then on.
But wouldn't it being stuck be new information?
With respect to the previous one, yes, but you couldn't really, I think you could imagine no life at that point, nothing, no useful work could be done.
Speak for yourself, we're living forever.
Yeah, that's it. Of course, as you approach that limit, you could always say that maybe your internal speed of processing also adjusts to that. So it's a bit like in relativity, when we spoke about if you're moving at a certain speed, your time is slower than with respect to a stationary person. But this is true for any process, any timekeeping device. So that means you're thinking, you could be saying, oh, my time goes slower, that's brilliant. So if I'm doing something enjoyable, if I'm smoking a cigar, it's now lasting longer for me.
But if I'm in the hellfire, it's
also lasting, exactly. I'm doing root canal treatment at the dentist. It also lasts longer corresponding. My thinking, by the way, slows down in the same. It's not that I'm now suddenly thinking, ooh, things have slowed down. No, because my brain has slowed down in exactly commensurate way. And I think it could be that you don't necessarily have to notice this kind of degradation.
So even in this sort of degraded state of the universe, things could still carry on. Consciousness could theoretically persist, but it's just
right
adjusted
up to whatever. That's right. That's right.
okay.
You just slow it down in proportion. That's right.
And so a final question to wrap it up. Is there any way that we can escape the death of the universe?
Yes, that is also an excellent question. And, people now talk about all sorts of scenarios that would have been complete science fiction in the past. But there are serious people now advocating, for instance, that we will never be able to solve necessarily our environmental problems. And the most likely solution could be that we have to already now colonize another planet. Now, 100 years ago, this would have been definitely science fiction. But now, as you know, people are planning. They're saying, what if we, how do we establish a colony on Mars or some other place, of course? If our technology improves, maybe we can go even further than that.
Beyond the universe, do you think?
Indeed. And now if you extrapolate this way of thinking, the question is, will we ever, if we understood, for instance, how our universe was created, is it possible that we ourselves could come up with a technology, with an experiment that could create another universe? Maybe that's kind of the ultimate form of escapism in that sense. And who's to say? We really don't know.
Well, on that note, Vlatko, thank you so much for joining us. This has been one of the most interesting discussions I've ever had.
Thank you. Thanks very much for having me. Great pleasure.